So come by then if you still have regrades. Let's see. All right, with nothing else, you notice that, of course, I always review. I know a lot of you weren't there Wednesday, that's fine. I'm going to do a broad review. And so that's some review material. I'm going to get to that in a minute. I want to step back a little bit as I do a review of kinetics and point out that this is the simplest reaction you could possibly have. But I swear to God, this is nuanced. This is more nuanced than you may realize, because here's my question. Is it stoichiometric or mechanistic? Which is it? Right? Now again, you're ever since you took your first chemistry class, hopefully in high school or freshman, you've done, even if it's isomerization, you've seen this. But my point to you is that it's never made, I don't think, correct me if I'm wrong, I don't know that it's ever been made clear whether you're just seeing products, reactants, or does this tell you a little bit about how the reaction actually occurs? It makes a big difference because it determines how we write the rate equations. Mechanisms determine rate equations, and then you integrate them into rate laws. I'm getting to that stuff on top in a minute. Stoichiometry just tells you what turned into what. Here's the thing. They may or may not be the same thing. And that is where this gets to be kind of a real pain. Now let me give you an example. You can imagine that this would be both stoichiometric and mechanistic. So you have three possibilities. It's either stoichiometric, again, just telling you what products and reactants are. What's missing is what goes on in between. It's mechanistic, which means it's perfect. It tells you everything. Or it could be both. Now, let me give you an example. Now, you may look at this and say, well, this has to be both, right? Because it's like an isomerization or a nuclear decay. Those are the two examples. What else could possibly cause this to not be both? Let me give you an example. Where this fails, where this is stoichiometric and not mechanistic. What if it works like this? Sorry, here, let me be more mechanistic-like. A meets A to form a complex that then turns into two B's. Right, you see? This is the mechanistic. So if I wanted to write stoichiometric and mechanistic, then I would do this. Now that would be both, because that tells you, if this is stoichiometric and mechanistic, it tells you that two A's have to come together to form a product. And that allows me to write the correct rate law. It's just that if that's the case, in a textbook, you're going to get that, which now is only stoichiometric and not mechanistic.
So the bottom one then was just stoichiometric.
No, hold on. All right. If A goes to B, again, you don't know, this absolutely, it always is stoichiometric. Things always have to be stoichiometric, because what the heck else am I communicating, right? But it's easy to think it's also mechanistic. In a mechanistic case, what happens in here, if this is stoichiometric and mechanistic, a fluctuation in energy, so this is like a isomerization, what would happen is A is floating around, let's say in solution, a bunch of solvent molecules would whack it over the head kind of randomly. It's like a bunch of bees flying around. It gets energized, and some diffusion of energy flows into it, and then it turns into B. Okay, stoichiometric mechanistic. If instead there's this guy, then stoichiometric and mechanistic, here's the mechanism. Two of these guys have to get together, and there has to be a flow of energy into it, and they make two B's. Right, now this is fundamentally different. One can do what it needs to do all by itself, but in this case that's not true. They have completely different mechanisms. They have completely different rate laws. And it's just that when you write out the mechanistic and stoichiometric equation, it's too tempting to do that. Right? Now you're screwed. Now you don't really know how it happened. You see my point? We tend to write reactions this way, but it may hide the mechanism. Now the reason that's important is because of this. Oh, I can see it at the back. Now I see why there's a problem. It's broken. Anyway. All right, if A goes to B, you have a rate expression And don't memorize this or anything, it's stupid, just words. Rate expression, which remember, I'm covering now what I did on Wednesday. We often like to look at reactants, define rates in terms of reactants, because you're always in control of reactants. So the time derivative of the concentration, minus because the derivative is negative, reactants react, they go away. So this derivative is negative, we like to put a minus sign so that the rate will be positive, and that's literally the only reason. I mean, whatever. Okay, here's the rate law. This is where the mechanism. Okay, this is the most important part of this entire section. It's like the kind of thing that's so important you might see it again. So the mechanism is in the rate law. So again, the time derivative of products or reactants is brainless, and I went over that on Wednesday. If you were here, just watch the video. But what do I set this equal to? What do I set this equal to? Because by itself, this is just mathematical junk. But when I set this equal to this, I'm able to integrate the rate expression, the rate law, and then I know that if I plot A versus time, I'm going to get a simple exponential decay. And if I observe that behavior, then my stoichiometric representation is also the mechanistic representation. So if you tell me this, and if I think that that's the case, I'm looking for this behavior. Okay, so now one other thing is I mentioned last time that the rate of a reaction is the reason that this works. It's actually an argument of probability. If you want something to happen, the thing that is doing the action needs to be there. And the more of those things that are there, the faster at which that event will occur. Now this transcends chemical kinetics. It applies to basically almost everything. Okay, now with that said, I think I put this as 2A goes to B, but I'll put this as 2A goes to 2B. It actually doesn't matter. Products actually don't really matter in these simple cases. They do if I'm doing consecutive reactions, which we're talking about today. Okay, now, in that case, the rate is still the time derivative of the reactant. Wait a minute. Anyway. But the rate law, because there's two actors present, it doesn't matter that it's the same thing. And then we'll do A plus B in a minute. It doesn't matter that this is the same, that they're the same thing. The rate law is now the square. And again, that's because it takes two to tango. And then again, all right, so that's still equal to the time derivative of the rate. I think I'm missing a half there in this particular example, so I kind of screwed up. But anyway, when you integrate it, you get this behavior. And again, I went over this last time. That is calculus you should be able to do. So again, just watch Wednesday's video. And this is called second order. And the first example is first order. And I'm not too worried about those terminologies. You can think of it multiple ways. Literally, it's squared. It's that simple. This is squared second order. That's to the first power first order. Another way to think about this is look at the rate constants. This would have units. We got to have 1 over time. And it looks to me like this would have units of 1 over mole, 1 over time. Whereas this one would have units of 1 over time. So that's another way to know what order. Okay, now second order looks more like a 1 over x behavior, which is kind of, it's not, if you showed me that and said that's exponential, I'd be like, no, that's not quite right. That looks more like 1 over x. Exponential is not so bowed. So I'll call that exponential, that's first order. And this is more like 1 over x, which is second order. Okay, so again, the point of this is you've got this expression of what's happening, but that doesn't necessarily mean it's how it's happening. You then take data, and you would probably see one of these types of behaviors, which you then fit to either this or that. Although I personally haven't been doing this long enough. I actually, this is what I used to do for my PhD. You show me this, at this point I did this a million times, I can tell you which one it is. And now you know how the reaction works. Now the important thing about knowing how a reaction works is that now you can manipulate it. Now, I know there's a lot of fundamental knowledge that people do, like I spent a lot of this weekend watching. I found this rather attractive woman from Cambridge who has videos on black holes, which is what my new thing is. And cool, right? So they're always investigating black holes and whatnot. I don't know that knowing that is going to influence a person's ability to manipulate a black hole or really do anything for anyone. But when it comes to chemical kinetics, I've been around long enough to know that when people figure out mechanisms, people are smart enough to manipulate it for our betterment, right? We know how to make things go better. Or it allows you to say, well, I've learned how this reaction works, but if I apply that mechanism to another reaction, it'll work better. Why is that important? Well, what's the product? Oh, the product is a chemotherapy. Let me tell you another thing. If you have some chemotherapy, some of the drugs are very complicated. They can be 20 steps, especially one was called Taxol. It's a breast cancer drug. That one was like 20 steps. Someone shaved off 2 or 3 steps, they made $1 billion. That's not a joke. They made $1 billion off of that. So figuring out how things work and manipulating them is not only something you can do, it's worth a ton of money. So yes, we do it. So again, this is, a lot of people actually teach this class with this stuff at the beginning, but I generally don't for reasons I don't quite know, but anyway. So there you go. All right, now here's another thing I wanted to cover. Oh, sorry, before let me say something else first. Okay, now let me give you, I'm just going to go over a few more dramatic examples of untangling the representation of a reaction from stoichiometric to mechanistic. Now, part of what my point here is that I've written something, and of course it's very generic. You tend to see things, a couple of things together, not just two. And it makes a product or multiple products, whatever. Now, I can tell you that I have a pretty strong opinion without seeing any data. I mean, look, I only have a bunch of letters in there anyway. Whether this is mechanistic or stoichiometric. What's your opinion? Is this mechanistic or stoichiometric? Remembering that I haven't actually told you anything or even identified what the chemistry is.
Stoichiometric.
It's stoichiometric because if it's mechanistic, if this is a mechanistic representation, what happens is you have an intermediate of A conjoining to B, conjoining to C simultaneously, and there has to be an influx of energy into that transient complex to cause the atoms to rearrange to D. Now here's another little thing I want to let you know. When reactions do occur, when bonds break and atoms rearrange, that process is generally on the order of about 10 to the minus 12 seconds. That's a picosecond. In other words, this happens really freaking quick. When a reaction is set up to go, it happens very quickly. But now let me tell you that what you're generally waiting for is, if this is true, if this is truly the mechanism, what you're waiting for is for the species to find each other. The rate that you measure is the rate it takes for these things to find each other and to have enough energy. That is what you are waiting on. When it does decide to go, it goes so quickly that it's like you wouldn't write a rate equation for that because it's just basically instantaneous. And that's a very small number. Okay, anyway, all right, now that's if this is true, this is a mechanism, this is what it means. A, B, and C simultaneously conjoin and happen to have enough energy to make D. There are some examples of this, but it is extremely rare. You can just think of it from pure entropy. What are the odds that 3 things come together in the right time, in the right way, and have enough energy? Right? 0. No, that is not what's happening. This is absurd. There are some examples, but they're incredibly rare. What more likely happens, so again, I don't want to say, it is possible, but it's unlikely. So that says this is stoichiometric. What is likely is something like this, and this is the point of today's lecture. If you would have A goes to B, A plus B, we go to make some energized complex, which then reacts with C. But reality is this would be very stable. It would be an intermediate. So that's what I mean by the letter I. You might want to write that down. This would form an intermediate that finds C, and then you got yourself a D. This is way, way, way more likely to happen than all three come together. I'm just kind of laughing because actually I knew a student who quit a research group. Anyway, she quit a research group because she was asked to design a reaction that did this, and she, after a year, said, it's not possible, and she quit. Anyway, my point being is I think the advisor should have not done that because of what I'm talking about right now. Anyway, so this is more likely. All right, now, it turns out that because this is really common, you often see chemical reactions with tons of things turning into other things. I'm telling you, though, that it is almost universally true that they work this way. So what I'm going to do is I'm going to start covering, this is like a sequential reaction. So today I'm going to talk about how to set up and solve sequential reactions. But first let me do A plus B goes to C. I didn't cover that one yet. So let me cover that. That's what I was starting on, and then I caught myself. I realized I wanted to go over. So that would technically be a third order reaction, by the way. And again, there's very few examples of third order reactions. Okay, let me do A plus B goes to C. And also terribly important, as I mentioned to you, there's graduate, I had a graduate level class on kinetics. And all you do is you set up every reaction possible, every mechanism, and study the rate law. You spend days, like I say, a whole class on it. I found it to be like, oh, another one of these, you know. Once you get the basic idea, it's all just, it's like a math class just with x's. Now you got an x squared. Okay, let's make it a natural log of x anyway. Yeah, integrating different functions, and you can do that all day. Okay, so this is a second order. And now notice that this is basic. I look at this and I'd say, oh, this is the same as 2A goes to B. Because it's A plus B goes, it's still two things. It's still second order. It should be identical. Weird, it's not. This is terribly different. So let me just set up, let's see, of course, let's pick A. Let's pick A to be our, this part. And then there will be a rate constant. Again, it'll be second order. And another thing I want to emphasize is the way you play this game is, all right, this part is let's write the time derivative of a reactant. Rate constant, remember that this guy's job is to get the units right. It can make it big or small. That makes it fast or slow, same thing. I should have said it that way, fast or slow. And then you write the concentrations of the things that participate. And again, you have to know the mechanism to know this part. And if this is mechanistic, then A goes to, so the mechanism, of course, is A finds B in a excited state and goes to C. And that's why I'm writing first order in A, first order in B, but the units are 1 over molarity times 1 over time, and that makes that second order. Okay, now, here's the next thing. Oddly enough, this is way hard to solve. Wikipedia has a good derivation. It takes about 20 minutes. I don't want to do it. It's just, why bother? It's just a math problem, and I hope you get the idea. You can integrate, you see, the point is that there's a relationship between A and B, right? They react 1 to 1, so that's part of the trick. And then there's another really weird math theorem you have to know. Anyway, blah, blah, blah. Okay, let me just tell you what the result is. The most important thing about this is knowing how to write the rate expression. It's always the concentration of things that are participating to the stoichiometry to which they participate in the mechanism. Okay, so look up the Wikipedia thing if you're really interested in, and here's the rate of B over the initial concentration. This gets a little complicated. Now, as I told you, this really is terribly different than the previous example of 2A goes to B. Really could not look more different. And I've always been shocked at that. In fact, I asked a few questions on the faux homework about this second order, because it does some really weird things. And anyway, I just want to point that out. So, okay, rate law, rate expression, rate law, matrix, 20 minutes later, look on Wikipedia if you're really interested, you get to that. Yada, yada, yada. Now again, I want to emphasize, hopefully you can see how you can have a whole graduate level class on this. There's so many different mechanisms of this. We're going to do sequential here right at the end. Differential equations, first order differential equations. Look in a 17th century textbook that solves it, and there you go. There's really thousands of these that you can do. Okay, now what's really odd about this, and this is what the point of the homework is you would imagine that you might start with the initial concentrations. If you have an idea that you're trying to react A and B, and then there's nothing too funky going on, that your intended reaction and the mechanism are the same thing. Remember, the stoichiometric reaction and the mechanism are consistent with each other. You would probably think, well, then I'll start with one, usually millimole. When you're doing reactions, you often do things around a millimolar scale, tens of millimolar. I do 10 millimolar of this, 10 millimolar of that. You see what happens, though? It's something really weird. What is this equal to? With equal starting concentrations? Huh? 0, right? So what do you get?
No reaction.
Yeah, it's really strange. Sorry, this takes me a while to write, and suddenly you're like that. Anyway, so this guy here on the left is equal to 0. All right. So where's your time dependence? Okay, now what does this apply? When is natural log 0? Right, so I try not to do this. I know I told you this since a year ago when we started, but it implies that. Okay, and what this means then is that the concentration of A is always equal to the concentration of B at all times. But of course it is, because they react 1 to 1. So you actually, this is really a weird case, and this is the only one that does this. You don't really get that much information out of this. It's kind of useless, but there it is. All right, now, it turns out though, here, I'm gonna keep working on the second order, because again, this is the most common thing. Now, I as a physical chemist, I am way unusual in the black sheep of the department because of how I like to set fires. Because I set a couple of fires. I didn't mean to. Set the trash can on. Oh God, I can't believe you say that on camera. Set the trash can on fire once. I actually do a lot of synthesis. For a physical chemist, never do synthesis. I do a ton of synthesis, so I actually know quite a bit about this. It turns out that if you're reacting A and B, every time I do this, I've legit discovered new reactions and products, and that I'm like the only physical chemist who's ever done this. I also know that you often would start with A equals B. It's a good starting point. You never end there, right? The whole point of doing this is I'm going to optimize. When you optimize a reaction A and B, you rarely find that you do 1 to 1. Now there's two reasons. One is that maybe one of the reagents, A or B, is like way expensive, like it's a protein. A is a protein, that's expensive. B is like a dye, that's cheap. In that case, you're gonna have lots of B. You're gonna try to drive the reaction. And you remember, what's the proper word? What am I, if I'm raising the concentration, I'm raising the what? Remember your chemical, I'm talking about last semester, by the way. I'm gonna put this on the final just to screw. Activity. Remember that activity? You're raising the activity of B, and that drives reactants to products. So we covered that last semester anyway. That website's still up, by the way, if you want to look at the cat pictures. So it turns out you often, I'm just going to pick B. I'm just going to pick B, it doesn't matter. Okay, you often have one in excess. For one of the reagents is expensive, and you're trying to drive the reaction. Number two, you're just trying to drive the reaction. So it's really this, I think that's 1 point, I don't know. Okay, now if that happens, what you can then do is say that the concentration of B over the initial concentration is basically 1. Now let me tell you, often a tenfold excess, that's, when I'm doing dye labeling, I'm usually doing around a tenfold excess. A lot of the chemistry I do, technically, I usually have about a twofold excess of at least one thing. That wouldn't be so very true, but when I'm doing tenfold excess, that's pretty true. Okay, if that happens, if you do things in excess, you have what's called, therefore, a pseudo first order. Okay, I hear this term all the time. Whenever I go to synthetic talks, I hear the term pseudo first order all the time because, again, it's actually quite rare to see A plus B done equal molar because, for, again, all the reasons I said. And it also allows you, when you're doing this, you can also do an analysis now. Now, the reason is let me just do a little math. Okay, let me start with the rate expression. Now I've got 1 over the concentration of A over A naught. I dropped a little T subscript from last lecture, by the way. I found that to be kind of confusing. Okay, that's minus the natural log of A over A naught. And this is still equal to, okay, now we're going to call this a constant. So, sorry, hold on, let me just write this out. This is whatever you set it up to be. Okay. Okay. So now what you can do is, and again, I can't emphasize enough, I see this happen all the time. If I go to lectures on any kinetics, I see this almost every time. You call this K naught. It's the pseudo first order rate constant. I hear this all the time. All right, now from here, again, just keep my use of the board. What have I got? I've got A. All right, so if it's pseudo first order, it should have a pseudo first order look to it, and it does. E to the minus K rho prime. Okay, so that's what you can do with it. So again, drive something in excess and watch the other, and you'll see it decay kind of with an exponential. Not only is that frequently how the reaction is done, but you can also analyze it now, and now you can get the rate. Otherwise, you couldn't do that. If you didn't flood the reaction with one of the reagents to either get the rate or just because that's how you do it, when you do it that way, you're pseudo first order, and now you can get the rate, and of course, you also can know things about the mechanism, and yada, yada, yada. So anyway, so I blabbered on about that. I know sometimes it's like, sometimes I get kind of frustrated because I'm like, I know, you've heard me do this several times, like, this is really important, but you're seeing it for the first time, so you don't know that yet. So it's also, well, it's kind of helpful though, so many of you engineers, I know that you're going to stay in the chemical industry, so you will see this again, so hopefully you'll remember that. All right, anyway, last bit, I want to start talking about consecutive reactions because that is very common. There's really not too many things other than like the production of ammonia, which is still, that's like the second most produced chemical in the world. Nitrogen gas, okay, we have plenty of nitrogen gas. Hydrogen from, you get that from oil, you extract hydrogen gas from oil. Put it in a reactor with nickel, I think, nickel or iron, and just heat the crap out of it, and out comes ammonia. Okay, cool. But not many things are that simple. A lot of things are consecutive. All right, now to introduce you to consecutive reactions and still dramatically emphasize this stoichiometry versus mechanism, let me give you this example. Now this is going to make your eyes bleed, by the way. And I'm going to go across the board a couple of times. A reaction that I don't know that anyone really cares about, back in the day of people, 50s, discovering that they could do meaningful experiments because we had reliable electricity and spectroscopy started to become interpretable. Quantum mechanics existed, right? No computers yet. Anyway, this is something people latched onto. as an example. They studied the heck out of it to get the rate law. Okay, now again, the rate expression is just the time derivative of one of the reactants with the minus sign. The rate law is what's really important because that tells you mechanism. Okay, now I would have what? What did you tell me? Let me get you started. H2, right? To the what power? Okay, first power, so I don't write anything. What else?
VR2.
Okay, to the,
First power.
yeah, first? Is that, yeah. To the 3 halves. Oh, sorry, let me look at my notes. I'm not done yet. VR2. Plus, K2. K2, why not? HBr. The product appears in the rate expression, which should not be happening. Okay, what do you get from this? Right, this is not an A plus B. This is not the mechanism. I mean, the stoichiometry is A plus B, but the mechanism is not. The mechanism is not hydrogen and bromine come together, get energized, and then fall apart into 2 products. That is not what happens. If that happened, we would have done, again, what I was leading you to do. But instead, we get all this jazz. That means that something crazy is happening. And that's the point. Now, what is happening is consecutive reactions. Now again, unless you go work at the ammonium factory, all of you engineers are probably going to be doing consecutive reactions. So let me walk you through this, and then I'll start showing you how to analyze a consecutive reaction. And as I mentioned, when it comes to consecutive reactions, what you get are coupled differential equations, which, unlike the 1950s, when they didn't have computers, you have computers, and what you do is go get software that solves it for you. Why do we not have computers? All right, let me tell you what happens though. Consecutive reactions. The Br does not react with H2, it falls apart. And that would be a pretty reactive thing. Bromine is scary. I'm scared of bromine. Okay, once it falls apart, it finds H2. All right, now when H2 fall apart, why am I not writing H2 going to 2H? What do you think?
Because it won't fall apart.
Yeah, that's ridiculous. H bonds are incredibly strong. Maybe it was like 9,000 degrees, all right, but it's not. Okay, so this happens, and what happens with bromine steals an H, okay? So it needs a little help to break the HH bond. Okay, now I got myself a free H, and that guy is very reactive because, again, it doesn't like to be without a bonding partner. Okay, so now I've got another HBr, so now I'm forming products. And you can imagine Br and H, if they find each other, will react. That'll be like instantaneous, so I won't even write it down. Okay, so these are productive. So let me put this as forward. And here's the damnedest thing. You can go backward. I haven't written these down. There's 2 more. You can go backward. The way you go backward is H plus HBr. Okay, so some of the intermediates can react with the product, and so that's destroying your product. And last is of course, the 2 BRs can go back to just right. So there's some kind of equilibrium. That's really what's going on. Anyway. Okay, now if you know how to set up all the differential equations, you can figure out that rate mechanism. Now let me give you a taste of this. We're not going to actually do this. Again, I did this actually in grad school. In grad school, we did not do this. Okay, step 1. Step 1. Now, it would be obvious that the Br, notice that I'm writing Br, not Br2, would be initial concentration of Br2 e to the minus K1, there'd be like what, a K1T. These would all have different rate constants, K1, K2, yada, yada, yada. Anyway, I won't even write that down. Okay, now, and folks, you don't even have to really do this part. So what you want to do is ultimately you want to get this as a function of the initial, of all the species involved, even the H, even the BR. So you want to get this as a function of all of these things. And as you can imagine, each one of these, what I'm trying to do is I'm trying to show you differential equations, and you solve them for this. It's a bloody nightmare. So what I'm going to do is instead of going through this example, which would take 3 lectures, that's what we did in grad school, I'm going to just show you some simpler examples, right? I just want to dramatically emphasize how something simple can give rate expressions that will make your eyes bleed due to an unbelievably complex reaction scape. The solution to which is, I'm going to start showing you how to do that, but I just won't go further with that specific example, again, because it's just kind of hideous. All right, so anyway, just wanted to strike home a bunch of points at once. And I do hope that all of this is useful to you, because anyone in the chemical industry is making chemicals, and knowing how they work is only done with kinetics. And once you know how it is universally true that it's worth the effort, knowing how reactions work is going to allow you to manipulate it to your betterment. Okay, now again, I'm not going to go over this guy further, because let's start simple. Let's start simple. This is obviously a consecutive reaction. So let's start with baby steps. Instead of something that hideous, let's do A goes to B goes to C. Okay. After we've done a couple of these, we'd be ready to tackle this in earnest. And we won't even get that far to be blunt, because I only got one more lecture. Besides, it just gets detailed. Okay, now there's a K1 and a K2. Now I'm writing a mechanism, by the way. I'm writing the mechanism out. Now notice what would the stoichiometry be? What would, if you were looking this up in the textbook, just trying to tell you what the heck happened, what would you see?
A to C.
Right, A goes to C, right? But if that's not what happens, you're not going to observe the right behavior. So I'm writing the mechanism. Besides, especially if I'm writing Ks, then I definitely have to be writing the mechanism. You don't see rate constants written into stoichiometric reactions. They just tell you what the products and reactants are. Anyway, okay, here's how this works. The time derivative of A with respect to time, minus sign, because it's a reactant, is going to be K1A. Okay, so first order. What we just saw, for those of you who are attending for the first time, what you saw at the very beginning, for those of you who were here Wednesday, that was on Wednesday. Exponential decay, very simple question.
So are we assuming that they're all rate constants? Because like above, when you had the forward and backward reactions, you don't have rate constants, you have equilibrium constants, correct?
Equilibrium, as I can actually show you next time, equilibrium, there really is no equilibrium. Equilibrium is when you have a forward reaction and a backward reaction, and they've reached a steady state. You can kind of, if you want to think about kinetics, you can completely never think about equilibrium. It doesn't exist. It's just a forward reaction and a backward reaction.
So we're using a forward reaction rate constant for a reversible reaction, and then you also have a...
Well, right. So instead of this, now this is a bit of an aside, so just, let's say you want to describe equilibrium. So this is not equilibrium, right? Because I'm drawing a mechanism, and those arrows mean A goes to B goes to C. So this would imply that the reaction yield is 100%. I'm not allowing it to go backward. Right? If you wait long enough, you're going to have 100% C. Okay, now, in an equilibrium case, let's say Okay, now, right, and this is a bit more realistic in all honesty, and I'll tell you how to deal with this next time, but I'll just go ahead, just because you're curious. You'd have to have this. Typically, the backward is a different rate constant, but just to make it clear that that these are associated, you often put a -1. Now, it's a completely different number. It's just so that you don't, when you're analyzing a situation like this, you have four rate constants. It's just that these two are clearly related in the way that these aren't, so you often put a little minus sign in front of them. Right. Now recall also that you asked about equilibrium. Well, the reaction is done. I'm not talking about that. I'm talking about at the beginning. Right? Now, did we ever cover how to figure out this kind of stuff when the reaction is over? Did we cover that?
I don't think so.
I am going to stab you with an narwhal tusk.
This semester?
Last semester.
Oh, last semester.
Yes, you did. Yes, you did. LNK is RT minus RT LNK delta G. Remember this? Right, so we have covered this. So I'm actually talking about what happens at the beginning of the reaction. So at the end of the reaction, I know how to deal with it. And again, I'm also going to cover equilibrium in this context. But I'm actually talking about the very beginning, before equilibrium has been set up. Huh? That's okay. All the time we have, let me just break this down real quick. Let me just tell you how you deal with B. Okay, B is a product. But what happens is, now remember, as a product, there's no minus sign. It forms as a result of the formation of A. So this looks simple too, but B can be lost. Let me show you how you deal with that. It's lost due to its own presence. Right, so positive source, positive expression, but there's a sink. The sink is itself. It minus, let me make that clear by doing this. Just like A is its own sink to form B, B is its own sink to form C. So that's how you do C. And then the rate of changes, sorry about this, is then of course B. Okay. And then the last thing you do is you take all this mess and you solve for C. And I will show you how to do that next time in this example, and that's basically the end of the semester. Right, this is the idea.